the CO2 concentration in the biomethane or biohydrogen is about 40%. So it is necessary to capture the CO2 with some porous materials. And so there are several CO2 separation technologies, such as the high pressure water washing, the chemical absorption, and the others. So we compare the membrane separation with the chemical absorption. So you can see the investment cost and the running cost of the membrane separation is much lower than the chemical absorption. But the product purity is similar at 99%. So this research focuses on the membrane separation technologies. And so this is the membrane unit in the industry. And so this is the mechanism of the membrane separation. So it is a hollow fiber membrane. So you can see the feed gas it is run through the membranes. And there are some gas, the penetrated gas is outside the membrane, and the residual gas is collected. So the hydrogen and the CO2 gas are the fast gas, and the methane is the slow gas. So for the traditional process, the pore size separate the different gases with different molecules. Because the hydrogen and the CO2 gas has the small kinetic diameter, so it is easier for the hydrogen and CO2 to penetrate through the membrane pores. But the methane has a higher diameter, so the methane is in the residual gas. So this is the traditional membrane for the pore size separation. But here I want to introduce a novel process, that is the solution and diffusing combined together. So it is a different mechanism. So for the membrane separation materials, there are several types, the polymers, inorganic, and hybrid materials. And for the polymeric membranes, there are several polymers. And here, the polyethylene oxide is a hot topic. It is also called the PEO. It is an organic polymer. You know, for the commercial interesting polymer membranes, at present, mainly focus on the inorganic membranes. But we can use the PEO to prepare the mixed matrix membranes, and it can be loaded with nanoparticles and to prepare the novel membrane materials. And so these polymer membranes has some advantages. It has the super film formability, the good processability, and mechanical properties. So the CO2 has a high affinity in the membrane because the polar ester group, and this material also has a highly flexible polymer chains. It has high free volume and high CO2 permeability. So this is the solution diffusing mechanism of the gas transport in polymers. So you can see this is, can you, excuse me, can you use the video? Hello? The video, can you click on the video? No. This one, click on. You click on the video, on this figure, yeah? Okay, no problem, I can introduce. And so there is a feed gas pressure. Yeah, it is the video, yeah. And so this is a feed gas pressure, and so you can see this is CO2 and this is the methane. Although the CO2 it has a high affinity to the membrane materials. So this mechanism is just like the Hawaiian dance, the girl's skirt. You know, the pore size is smaller than the CO2, but the CO2 molecules, when the CO2 molecules penetrate through the membrane, the pores can be changed larger. So the CO2 molecule is solved in the membrane and then penetrates through the membranes. So it is called the solution diffusing mechanism. So for the condition, the pressure of the feed gas is a small higher than the pressure of the penetrator. So this mechanism has several characteristics. The sorption on the upstream side and the diffusing down the pressure gradient and the desorption on the downstream side. So this is the PO-based mixed matrix membranes, and so this is a novel membrane, and the base material is a polymer. So here we use the PEO as the polymer matrix, but in the matrix there are some porous filters. So you know there are the hot material that is ZIF, the zeolinic imidazolate frameworks. So there are several types of the ZIFs. So zif-8 is very suitable as the porous filters. So for the zif-8, this is the typical structure of the molecule. So you can see the diameter, the inner diameter of the zif-8 is 11.6 A, and the window size is 3.4 A. So this zif-8 is suitable to act as the porous filter. And there are also several polymer matrix, such as the PGDA and PEGMEA. And the PGDA can also be quick-linked and to prepare the XL PGDA. And also the PGDA can combine with the PGMEA. So we use the polymer matrix to be loaded with the zif-8 porous filters. So this is the SEM cross-section images of the zif-8 PGDA. So you can see the 10% to 50% of the zif-8 is well dispersed in the mixed matrix materials. And so we also detect this is the XRD pattern of the zif-8 PGDA membranes. So you can see the increase in D-spacing meant the increase of the distances between polymer chains and then the increase of the free volume. So when we adding, so you can see without the zif-8, only the PGDA membrane, the CO2 permeability is about 130, and the gas selectivity for the CO2 to hydrogen is 7.8, and the selectivity for the CO2 to methane is 20, and the CO2 to nitrogen is 55. But if 10% of zif-8 is loaded in the membrane, so the CO2 permeability is increased dramatically from 130 to 320. So the permeability of the CO2 is increased by 150%. But the gas selectivity of the three is similar to the original. So that means the 10% of the zif-8 loading is a good choice to increase the permeability dramatically. And if we use the PGDA and combined with the MEA as a mixed matrix membrane, and you can see the CO2 permeability can further increase from 330 to 560, but the selectivity is almost the same. So the permeability capability is become better than before. And so this is the detection parameter of the CO2 solubility and the CO2 diffusibility. So you can see the solubility of CO2 to methane is about 10, and the diffusibility of the CO2 to methane is about 1.9. But if 10% of zif-8 is loaded in the membrane, the solubility decreased, but the diffusivity is increased. So the if 4 multiply with 4.7, so the result is similar to the original. So that means the selectivity of the CO2 to methane is similar to the original. So that means the introduction of zif-8 nanoparticles in the membrane increases the CO2 permeability dramatically, but has little effect on the selectivity of CO2 to methane, CO2 to hydrogen, and CO2 to nitrogen. So we use the Lewis-Nielsen model to predict the permeability, and we found, you can see the red curve and the blue curve are the calculation result, and the dispersed dot as the experimental result. So you can see the CO2 and the CO2 to light gas selectivity in the membrane can be satisfactorily described with the model, but the model underestimates the gas permeability because the zif-8 nanoparticles increase the distributions in the polymer. Okay, the conclusion is introduction of zif-8 nanoparticles in the polymer increases CO2 permeability with minimal effect on the selectivity. Adding 10% of the zif-8 into the cross-linked PGDA increases the CO2 permeability by 150% without the reduction of the selectivity. So thanks for the group, and thanks for your attention.
Questions for our speaker? Yes. So maybe just a bigger picture question. So I'm curious what you think the advantages of using, let's say, a membrane over, liquid contactors or other kind of sorbent configurations. Where do you see this being applied in industrial processes?
For the industrial application, at present, for the middle and small scale application, such as the biogas, the methane purification, the membrane separation has more advantage than the chemical absorption because the low investment cost and the operation cost. But if for the coal-fired power plant, the large-scale industrial application, the chemical absorption has a lower cost. Yeah. So.
I don't know much about this, but do you know if there are membrane-based technologies deployed right now?
There is a critical limit of the gas flow purification. If 20 cubic meters per day, if the gas flow is less than 20 cubic meters a day, it is suitable to use the membrane separation. But if the gas flow is much higher, the chemical absorption is best. Okay?
I have one question. I'm actually surprised that the zif-8 didn't change the selectivity, because it looked like you showed that the pore size was larger than, for example, hydrogen CO2, but it's smaller than the methane molecule. I expected it actually improve the selectivity just by confinement of that pore, but that's not what you found. Any reason why you think that might be the case?
For the traditional membranes,
Yeah.
the pore size is used to separate the different gases.
Yeah.
So the hydrogen can be penetrated through the small pores, but the CO2 cannot.
That's what, yeah.
But here, the CO2, because we use the organic polymers, as the MMN, so the CO2 can be penetrated through the pores, but the hydrogen cannot penetrate the pores. So this is the advantage of the solution diffusing mechanism. It's different, The bigger molecule can penetrate.
Yeah, that's surprising to me.
Yeah, this is interesting. Yeah.
Any other questions? Yes.
Yeah, please.
I saw very interesting figures you just presented. So the PO membrane
Yes.
is very uniform zif-8 figures.
Yeah.
So
You mean the SEM photo?
Yeah.
Okay.
So how do you control the uniformity of the pore structure?
The PO is used as the mixed matrix membrane, and the zif-8 is loaded on the memory. So that depends on the experimental process. And here I didn't show very in detail, but it has published in the chemical engineering journal. Yeah, you can see it. Yeah. So the zif-8 nanoparticles can be well dispersed in the membranes. No problem. Yeah. Okay. Thank you.
Any other questions? Let's take your speaker one. Thank you very much.
Thank you.